Welcome to our demonstration of the Deep Space File Transfer Protocol, or DSFTP, for CP372 computer networks. This assignment required us to implement a reliable data transfer protocol over UDP, the same layer that real deep space communication systems use, where packet loss and delays are common. The project is organized into two separate directories, sender and receiver. Each one contains our implementation file, along with two provided utility classes. We compile both sides independently using Java-C. The sender is responsible for reading the input file, breaking it into 124-byte chunks, and delivering them reliably using the either stop and wait or go back and depending on the command line arguments. The receiver listens for incoming packets, buffers out of order data, sends cumulative ACKs back to the sender, and writes the reconstructed file to disk. Both sides must be compiled before running. We always start the receiver first, since it needs to be listening before the sender initiates the connection. The receiver command takes 5 arguments. The first is the sender's IP address, in our case 127.0.0.1, which is the localhost. The second is the sender's ACK port, which is 5001. This is where the receiver will send ACKs back to. The third is the receiver's own data port, 5000. This is the port it listens on for incoming packets from the sender. The fourth is the output file name, where the received data will be written. And the fifth is a reliability number, RN, which equals to 0 here, meaning no ACKs will be dropped. Once the receiver is running and listening, we launch the sender. The sender command also takes 5 required arguments, with an optional 6. The first is the receiver's IP address. The second is the receiver's data port, 5000, which is where the sender will send all its packets. The third is the sender's own ACK port, 5001, which is where it listens for ACKs coming back. The fourth is the input file to the transfer. The fifth is a timeout in milliseconds. We're using 100, meaning the sender will wait 100 milliseconds for an ACK before retransmitting. The optional 6th argument is the window size. If omitted, the sender runs in stop and wait mode, which is what we're doing here. The first thing the sender does is send an SOT packet, start of transmission, with type 0 and sequence number 0. This is the handshake. The receiver responds with ACK 0 and the connection is established. Once all data is sent, the sender transmits an EOT packet, end of transmission, with a sequence number equal to the last data sequence plus 1, modulo 128. The receiver ACKs it, closes the output files, and exits. The sender then prints the total transmission time from the moment the SOT was sent to when the EOT ACK was received. We can verify the transfer was successful by checking the output file in the receiver directory. It contains the same content as the input file on the sender side, confirming every byte was delivered correctly. Now we demonstrate go back end with a window size of 20. The command is the same as before, but with the window size added as the 6th argument. Without the argument, the sender defaults to stop and wait. In GBN, the sender maintains a sliding window and sends multiple packets without waiting for an individual ACK. You can also see the chaos engine permutation in action. Packets are sent in groups of 4 in the order of I plus 2, I plus 3, I plus 1 to simulate out of order delivery. The receiver handles this by buffering packets that arrive out of order and only delivering them to the file once all preceding packets have been received. It then sends out a cumulative ACK for the highest in order sequence number delivered so far. Notice the transfer completes significantly faster than stop and wait for the same file because the pipeline is kept full instead of sitting idle waiting for one ACK at a time.
This scene demonstrates ACK loss handling. The receiver is now started with RN equals 5, meaning Chaos Engine will drop every 5th ACK it would have sent. This simulates a lossy network link. With stop and wait, you can see timeout messages appearing regularly in the terminal. Each time an ACK is dropped, the sender waits the full 100 milliseconds before retransmitting. Since there is no pipelining, the entire transfer stalls during each wait. This is why stop and wait is so sensitive to packet loss. The timeout overhead accumulates across thousands of packets. Now, watch the same scenario with go back end. When an ACK is dropped, the sender eventually times out and retransmits the entire window from the base. But because it was already pipelining many packets, the receiver likely already buffered several of them. The window recovers quickly and the overall impact on transfer time is minimal. This is the core advantage of pipeline protocols under lossy conditions. Here is a close-up of the full protocol lifecycle for one complete transfer. You can see each phase clearly in the terminal output. First, the handshake. SOT is sent, ACK received, connection established. Then data transfer. Packets sent with sequence numbers, ACKs received, window advancing. Then teardown. EOT sent, EOT ACK received, transfer complete. The total transmission time is printed at the very end. That concludes our demonstration of the Deep Space File Transfer Protocol. We successfully implemented both stop and wait and go back end over UDP in Java, with full support for ACK loss simulation, out of order delivery, timeout handling, and correct file reconstruction. Thank you for watching.